Hello everyone. Today I will start one most important characteristics. We will discuss the characteristics which is important for textile material, which is evenness. So, evenness means that whether there is the material is even or not, or there is any irregularity is there or not. So, textile material, particularly the staple yarn, we cannot produce without any irregularity. So, we will discuss all the aspects related to irregularity of textile material. So, first we will discuss that the evenness in yarn, what does it mean? So, evenness actually mean that variability in property. Okay. That property may be in terms of linear density, that is mass per unit length, may be due to the diameter, variation in diameter, variation in twist, thickness, that means its diameter. If it is not circular, then you can call it as thickness, strength. So, there are wide range of variabilities, but most important variability which affect all other characteristics is variation in mass per unit length or in variation in diameter, which are interlinked. Okay. So, in our discussion here in this topic, we will discuss the variability in textile yarn, particularly spun yarn, in terms of mass per unit length or in terms of diameter, and twist, thickness, strength are directly related with these characteristics, with the variation in mass per unit length. So, the most popular approach is to measure the variability in mass per unit length. Okay. That is the most popular approach. So, most of the testing instruments which measure the variability in yarn, they are in terms of either mass per unit length or in terms of diameter. So, first let us see the variation in mass per unit area, unit length, sorry. So, that is called the basic irregularity. So, that why is it basic irregularity? Because all other irregularities are directly or indirectly related with the variation in mass per unit length. So, what are the other irregularities which directly depend on this mass variation? These are twist variability, strength variability, diameter variability. Now, if we see the variation in twist, how is it related with the variation in mass per unit length? So, this is one yarn, staple yarn. Okay. This is a yarn strand. So, it is a fiber strand, it is coming out from the front roller nib of drafting system. Now, when we impart twist, so in this portion A, this is portion B, say C, D like this, we can divide into different zones. So, in zone A, the number of fibers in the cross section is large number high, and in zone B number of fiber in the cross section is less. That is why it has got mass variability. If we take the mass of zone A, it is m, say m 1, m 2, if we cut this. So, the mass of zones will be different. Now, here this yarn has got very high mass irregularity, mass per length irregularity. Now, if we apply twist on the strand, so as zone A has got large number of fiber, okay, the torsional rigidity of this zone will be much higher than zone B, because here number of fibers in the cross section is much less. So, when we apply twist at this point, so the twist will not be distributed evenly throughout the yarn. Suppose let us see another situation where it is a filament yarn, number of filaments are exactly same, okay. This is filament yarn, and here if we apply twist, as number of filaments are same, the torsional rigidity of each and every point are almost same. So, the twist will get distributed evenly. So, as mass variation is not there, so here twist variation will also not be there. Okay. Now, but the situation is different for staple yarn case with very high mass irregularity. So, twist flow will be entirely uneven, that means maximum twist will be at the zones where number of fibers in the cross section are less, because of the high lower torsional rigidity. That means, this twist variation will be there, and if we measure twist, it will have very high twist variation. Okay. Now, the zone A or zone C will have soft twisted portion. So, as these are soft twisted portion and this point is hard twisted portion, that means rate of reduction in diameter due to twist will be much higher here than zone A. That means, the diameter variability will also be exaggerated. So, here this portion will have very high diameter, and accordingly this portion zone B will have less diameter. So, diameter variability is also directly dependent on mass variation. Even if the twist variation is not there, suppose twist variation is not there, still this portion A will have higher diameter than portion B. If we assume there is no twist variation, still A and C portion they will have higher diameter because of the presence of larger number of fibers, higher number of fibers. Okay. So, that is why the twist variation and diameter variation, they are directly related with the mass variation. Still another characteristics, the strength. So, this strength of zone A will be definitely higher than zone B, because number of fibers in zone B is much less than the fibers in zone A. That means, the strength in the yarn is carried by the fiber. So, as the number of fibers are less in zone B, so this zone B or zone D, these zones will be the weak point. Okay. So, and the yarn that breaks at the weakest point. So, the strength of the yarn will be lower if the mass variability is high. So, the variability, mass variability, it is the twist, strength, diameter, they are directly dependent on the mass variability of the yarn, spun, particularly spun yarn. So, this is because mass per unit length is proportional to the number of fibers in the cross section. Okay. So, variation in number of fibers are the factor influenced by the draft. So, due to problem in draft, maybe due to eccentric drafting roller or maybe any other problem, slippage in the drafting zone. So, that causes the mass variability. So, any improvement in drafting or spinning system will improve the variability in terms of mass per unit length. So, if there is any variability, any mass variability, so we have to actually improve upon the drafting system or different spinning processes, so that the mass variability improves, and as if we can control the mass variability in the strand, then we can control directly the twist variability, diameter variability and also the strength variability. They are directly related with the mass variability. Next type of variability is the diameter variability. Okay. As I have already mentioned, they are directly related with the mass variability, and mass, the diameter variability is extremely important as far as the appearance is concerned. Now, let us see another situation. So, yarn A has got mass variability. So, suppose we have produced one yarn. So, let us imagine this is one yarn. Okay. Now, here the number of fibers in the cross section, the staple fiber, I am trying to draw. Somehow the number of fibers in the cross section here in zone 1, it is very high. Here it is there is a loose packing, although loose packing is there, but zone 2 has got less number of fiber, but the diameter is same. So, here higher number of fibers. So, same diameter, but mass variability is there. So, this actually this will not, although there is high mass variability, but as the diameter is uniform, in that case we can have fabric with uniform appearance, at least in the gray state. Okay. So, that diameter variability is also important. Suppose another yarn, we can have another yarn where so diameter variability is there, okay, very high diameter variability, but number of fibers in the cross section, if we see, so 10 fibers also here, and here also 10 fibers. So, this throughout the cross section, suppose I am having say 10 fibers in the cross section, you take. Now, if we measure the mass variability, this yarn will give extremely excellent result, very good result, but if we measure the diameter variability, this will be very inferior quality yarn. Now, if we see the appearance wise, this yarn will fail, this yarn will pass, but as far as the mass variability, so this yarn will give excellent result. So, we have to see which measurement technique we have to adopt. So, that depends on various factors, these things we will discuss here. Okay. Now, although mass variability gives indication. So, if suppose this yarn A, yarn B, so yarn B we can visually see it is a variation, okay, that we can always reject, but in this yarn suppose as far as mass diameter variability, this is giving very good result, diameter variability is not there, but the thing is that if we produce fabric out of that and after dyeing there will be total uneven effect, unevenness in the fabric, patchy dyeing will be there. So, this will create problem in later state, although the diameter variability is not as. In that case it is, if we test in terms of mass variability, then that particular instrument will show this is the inferior quality yarn. So, that whether should we go for diameter variability or mass variability, we have to select depending on our priority. So, variability in diameter is important because of its profound influence on appearance of the yarn. So, appearance of yarn as well as the final product fabric. Okay. So, it can be easily perceived by naked eye. Okay. So, latest models of evenness tester, they actually test the mass variability along with the diameter variability also. Okay. So, that two types of approaches are there, we can adopt any of the approach or both the approaches. Okay. So, diameter variability, as I have mentioned, it is directly related with the mass variability. So, if we test diameter variability, we can guess, we can actually most of the cases diameter variability directly shows the mass variability. So, what I have explained earlier, those are the ideal case. So, but it is not, it does not happen when mass variability is there, that directly show the diameter variability. On the other way, if we measure the diameter variability, that will show the mass variability also. As I have already explained, as twist has a tendency to run into the thin places, the variability in mass gets exaggerated in the diameter variability. So, it shows off in the diameter. So, if there is any mass variability, means the uneven distribution of number of fibers. So, that will indirectly show the diameter variability, as twist will get distributed unevenly. Next comes the twist variation. So, twist variation is also an important aspect for measurement, but normally in terms of as the twist variation measurement, it is difficult, we cannot measure at very fast rate, but if we have any idea about twist variation, that will help us in actually predicting the performance or the quality of product, like the performance of yarn and fabric dyeability or defects directly is influenced by the twist variation, because as twist variation is there, the portion with less twist will have weaker place and soft in nature. So, from those portion with a low twisted portion, fibers will start coming out, and these fibers may form hairs or peels in the fabric. Also those portions will be weaker in the strength, okay. And also the dyeability, if the yarn has got high twist variation, like suppose this is a yarn, okay. In this portion it is a high twist is there, and in this portion the twist is less. high twist. So, as we have discussed earlier when we discussed the twist. So, the higher twist angle, this is higher twist angle, this is low twist angle. Higher twist angle will have say higher twist multiplier and this portion will have less twist multiplier. Higher twist multiplier means this portion will be compact and here this portion will be loose in nature. So, what will happen that if you try to dye will not penetrate in this zone easily and here in the same yarn in other portion it will dye will be actually will penetrate and this portion will be dyed with the darker shade. So, that due to twist variation we have the yarn with uneven dyeing. Also the twist variation will affect in other way that because this portion with high twist state will reflect light in different way than this portion. This portion with a less twist will have very shining in nature. So, this affect the fabric appearance. Okay. So, soft end are major causes of breakages. So, that in the soft end in the preparatory process of weaving and loom set. So, the low twisted portion will cause most of the breakage. Okay. They arise from low twist variation. Soft twisted yarns take more dye. So, uneven dyeing is caused by high twist variation as I have just explained. Weft bars and bands are also caused by low twisted yarn. So, if there are low twisted yarn and it is going in the weft, so that will cause. So, if it is the twist variation is in the longer length, so that will cause weft bars. Weft bars are visible for dyed yarn definitely, because that low twisted portion will absorb dye higher quantity, but in case of grey quality without dye that also affect show the weft bar because of the uneven reflection. So, the low twisted portion will reflect differently than high twisted portion. So, clear weft bar will be visible in the fabric, and twist variation mainly in the yarn is actually generated from slack spindle tapes or jammed spindle. So, if there is any jamming in the spindle, because the twisting comes from the rotation of spindle. So, if spindle variation spindle rotation is uneven, that will directly create the twist variation. Next come the strength. So, as we have discussed, the strength variation is directly related with the diameter variation or mass variation, okay. And higher unevenness of yarn, that means unevenness in terms of mass variation or in terms of diameter variation will have higher strength variation. So, also on the other hand, if a yarn has very high strength variation, that will actually result in poor performance of the yarn, because breakage rate will be high. So, yarn breaks at its weakest point. So, yarn with high strength variability, as we have discussed in detail in last segment where we have discussed the strength section. So, strength variability, actually higher strength variability will result the higher yarn breakage rate during processing. So, it breaks at weakest point. So, yarn with high strength variability will result in high breakage in further processes like winding, warping, sizing. Okay. And we have seen these two equations. We should remember this equation. In this equation, which shows that the variability, this is the variability, this is Cb percent. This shows as the Cb percent increases, the yarn strength, keeping all other parameter constants, R constant, R means the times the length gauge length increases, if we keep r constant. So, in that case if we see, as the yarn strength variability increases, its strength decreases. Okay. Similarly, for dynamic running in process, in say winding warping process, as we have seen, the if say for a same yarn strength, mean strength x bar is the mean strength of yarn in static mode, and T is the tension required for certain number of breakage per unit length of yarn. So, if we keep x bar constant and the strength variability, this is standard deviation of strength, the sigma, if it increases, then the tension required for certain number of break will reduce. So, that means yarn performance will be poorer. Okay. So, strength variability is partly dependent upon the count variability, that we have already discussed. Count variability means the variability in mass per unit length, and partly upon spinning condition and mechanical defects. So, in case of any mechanical defect, even spinning condition is poor, then also we will have high strength variability. Like if due to poor spinning condition, suppose the twist variation is there, and twist variation, if twist variation is high, then it will affect the variability in strength. Next variability is the variability in hairiness. So, hairiness variability is high. Variation in hairiness leads to streaky warpway appearance or weft bars. Like suppose this is a fabric and it has been produced by yarns with high variability in hairiness. Suppose this portion, this is weft, this portion the hairiness is good, there is no hairiness or less, and this portion when it is weaving it is a high hairiness. So, that means this will give clear weft bars, because this portion with low hairiness will have proper reflection, regular reflection. This portion will actually scattered light, and this portion will look dull, and this. So, that band will be there due to the variability in hairiness. So, weft bar, clear weft bar will be there, and also if it is in the warp, there will be streaky bars will be there. So, that is actually clearly visible from the fabrics. So, more light will be scattered from the portion of weft where hairiness is more, and this leads to weft bar, and high hairiness disturb weft shade formation during weaving. So, that also result poor quality of fabric, and breakage will be there, and stitches and floats will be there. Okay. Now we have to express, we have to now measure the hairiness. So, normally in yarn, staple yarn, we express the hairiness, we express the evenness in by two terms. One is it is by CV, coefficient of variation, which is nothing but standard deviation by mean multiplied by 100. Okay. That is in terms of coefficient of variation we express. Another way of expression is the percent mean deviation, which is nothing but it is u percentage, commonly known as u percentage. It is a mean deviation by mean multiplied by 100. So, this is the expression, it is in terms of percent, and this one is the mean deviation, that is x minus x bar. So, mean deviation, what is that? This is the mean deviation. So, it is a x minus x bar within mod. So, we will take the positive part, okay, this unit and divided by n. So, this is called mean deviation, and if we take the percent of that percent with x bar mean. So, that then it will be we will call it as percentage mean deviation, and this is one of the most popular way of expression of yarn evenness in terms of percentage mean deviation. Okay. When the distribution is normal, so in case of normal distribution, if we assume the distribution in mass variation is normal, in that case the relationship, rough relationship between C v percent and u percent is, it is a C v equal to 1.25 multiplied by percent mean deviation. So, if we know the u percent, if the instrument measures the u percent, then we can convert it to C v percent, and if the instrument measures both u percent and C v percent, we can check that it is approximately close to 125. It may not be 1.25 because this the distribution, the data may not be normal distribution, okay, but the data definitely it will be close to 1.25. Okay. Now, coming to the concept of limit irregularity. So, we must understand the concept of limit irregularity. So, in staple yarn, this concept of limit irregularity is there in case of staple yarn production, okay, yarn production from staple fiber. So, suppose this is one strand, this limit irregularity is valid for not only for yarn, for other form of material, continuous material, that is the sliver, it is valid for roving also. Okay. What is this? The fiber, staple fiber, these are distributed inside the structure. Okay. Now, if we assume the distribution of staple fiber within the structure like yarn, sliver, roving, those are perfectly uniformly. So, we are actually distributing the fibers whatever maximum possible even way possible, that we are distributing. Ideally, we are placing the fibers. We cannot make more even than this system. Theoretically, we are placing perfectly. So, if we are doing this thing, then the whatever irregularity we will be getting, that irregularity is, it is called limit irregularity, where we assume our spinning machines are running exactly ideally, like drafting. These are the drafting rollers. In spinning, we have seen large number, the material goes through large number of pins, drafting rollers. So, this drafting rollers, there is no problem at all, no problem. They are perfectly circular, there is no slippage, running perfectly, setting is exactly perfectly. Okay. In that case, whatever fiber strand it is producing, it is perfect. But the individual fiber like cotton fiber, it has got unevenness, wool fiber unevenness in diameter, those variations this machine cannot do. The spinning machine cannot make the individual cotton fiber even. This is the nature of the fiber. Okay. Now, this type of irregularity will be there, okay, due to the variation in diameter, in inherent mass per unit length variation, but the spinning machine has done its job. There is no such defect. Even the environment, whatever environment is there, humidity or temperature, they are exactly perfectly maintained. In that case, whatever the yarn, whichever yarn we are producing, that means we cannot produce better than this, and that, and still this will have certain irregularity, because it is a staple fiber, it has got random arrangement of fibers here. So, we cannot produce better yarn than this. So, this and whatever variability this yarn has got, it is called limiting irregularity. Okay. Limit irregularity, that means by definition it is a most uniform strand of material which our present machines can produce theoretically, is one in which the fiber ends are laid in random order in sliver. It is not the preferential order. The order of arrangement will be exactly random, there is no preference, no unevenness. So, that in the order in the sliver, roving or yarn, that irregularity is known as limit irregularity. It is a best possible product. Okay. So, its fibers ends are laid in random order. Okay. For such a strand of material, the irregularity is given by the formula. So, this is the definition of irregularity, and now we have to calculate the irregularity, limit irregularity. This is the formula, where VR is the limit irregularity in terms of CV percent. So, VR equal to, so this is the irregularity of this portion, it is a VR square equal to 100 square by n, where n is the number of fibers. Suppose here it is a n number of fibers are there, because why n, as we have seen that the variation in number of fibers are there in yarn cross section. So, variation in number of fibers are there in normal case, normal yarn. So, here higher number, this defect, the distribution is due to the problem in spinning machine. Spinning machines could not distribute the fiber evenly, that is why it has distributed here, say N 1 fiber, say N 1, N 2 number of fiber. So, where N 1 is more than N 2, but our assumption is that spinning machine is running perfectly. So, it has distributed the fibers evenly, it has done its job, because spinning machine can do this much, it can actually distribute the number of fibers in the cross section. Okay. So, it has distributed, because our assumption is that spinning machine is running perfectly, ideally. So, here throughout the cross section the number of fibers are n. So, in that case, so limit irregularity VR equal to 100 square by n plus Vm square by n. What is Vm? Because it has done its job, n number of fibers it has actually laid on the surface, but this Vm is the variability in fiber itself. As the individual fiber, like cotton fiber, it is a mass variability, mass CV of cotton fiber. So, mass CV of cotton fiber, it is a Vm, it has got two terms, one part straightway based on the number, okay, based on the number and the arrangement. Okay. It is perfectly arrangement is there, but due to the this discontinuity and all this, it has got this portion, and second portion is basically due to the individual fiber variability, okay, individual fiber mass variability. Now, can we have a fiber with least mass variability? Because we have seen natural fiber will have very high variability, definitely we cannot control. Can we control this? Yes, we can control that. If we take say synthetic fiber, man-made fiber like polyester, cut polyester fiber, where the fibers diameter or mass variability we can assume as almost 0, there is no mass variability. So, in that case this Vm for synthetic fiber, Vm will be 0. So, this portion will be 0. In that case V r square equal to 100 square by n, or V r equal to 100 by under root n. So, this is for synthetic fiber. For synthetic fiber, the limit irregularity is 100 by under root n, because why is it 100? This portion, as I have already mentioned, this is the system, because it is a, this one is the discontinuous fiber, and discontinuous fiber whatever way we arrange, there will be little bit unevenness. So, this unevenness is, this is called limit irregularity. So, this is the portion, this as we have already discussed here, and V r is a limit Cv% of mass per unit length. This is V r, it has got two components. So, n is the average number of fibers in the cross section of the strand. Okay. This is the average number of fibers in the cross section. So, that cross section, in the cross section ideally there must be n number of fibers everywhere, but there will be definitely some variability, that is why mean number of fibers are taken here. And this second part, as I have mentioned, it is the actual Cv of fiber mass per unit length, this Vm. So, if we can make it 0, that is for say synthetic fiber, this portion will be V 0. So, in synthetic fiber or man-made fiber, Vm is 0. So, this equation, this relationship has been reduced to 100 square by n. Now, what will happen to cotton? Cotton, you can say V r square equal to 100 square by n plus V m square by n. Okay. Now, for cotton, if we can measure the mass variability, if we can measure, then we can get the this value for, and this mass variability for cotton, it is very high. Here if you see the mass variability of cotton, it is basically around 35%. So, this mass variability cotton, as it is a natural fiber, in it is a natural fiber. So, if we see the Cv%, if we measure the Cv%, it is a approximately 35% here. And see, that is why for cotton, this is the, for cotton 100 square by n, Vm c square by n, and this is the mass variability of cotton, and the typical formula for normal cotton, for typical cotton, the formula is the its V r square equal to 106 square by n. So, this is the formula for cotton, and how this 106 has been achieved, because as I have mentioned, from large number of experimentation, it has been observed that cotton has got average, the mass variation is around 35%, and if we put 35 here, then this total value will be 106 square. So, if we see, and we have measured, so that means for cotton, if we see it is a 100 square by n plus this is 35.16 square by n. So, n 100 square plus 35.16 square, this will be, it will come out to be 106 square by n. This value will be approximately 106 square plus n. So, V r for cotton will be 106 by under root n. This is the general formula, we can remember this one. So, for calculating limit irregularity for synthetic fiber, we have to use the formula V r equal to V r for synthetic, 100 by under root n, and for cotton it will become 106 by under root n. So, this difference from 100 and 106, it is mainly due to the variability of mass variability of cotton. Now, what happened to wool? So, if you see the wool fiber's variability, mass variability is much higher than cotton. So, wool's fibers variability is around 50-55%. This is the variability of cotton. Now, for wool, this mass variability of wool, due to that the equation become 112. In case of cotton it is 106, for wool it has become 112. This is mainly due to high value of variability, mass variability of wool, it is around 50%. So, if we see for wool V r wool, so it was V r cotton, V r wool square equal to 100 square by n plus 50.44 square by n. So, if we take n equal to 100 square plus 50.44 square, equal to 112 square by n. So, that means this value comes from this condition. So, this is this 50.44, 50, 51, this variability, mass variability of wool is at this range. We will see in next slides, the diameter variability can also be measured for wool, it is coming out to be around 25%. So, one can remember the 25%, around 25% is the diameter variation of wool, I am talking about individual wool fiber, and mass variation of wool is around 50%. So, from that assumption this value comes. So, one can directly use this formula. Now, what will happen in case of blend? If we blend polyester and cotton, for polyester we have seen the limit irregularity is 100 by under root n. For cotton it will become 106 by under root n. So, apparently people may think that if we blend, the irregularity should be in between 100 and 106. So, for polyester it is V r equal to 100 by under root n. For cotton V r polyester, V r cotton 106 by under root n. But if we mix VRPC, is it between 100 and 100 to 106 by under root n? No, because when we blend two entirely different types of fiber, that means there are other problems will be there. That means cohesion between fibers, clustering will be there, movement through the drafting roller due to the frictional contact between fibers. So, this will affect the variability adversely. So, that means the variation, the limiting variation will be higher than, much higher than this. Okay. So, for blended yarn, for blended say polyester cotton yarn, this will be typically 118, that has been actually observed. So, this is the limit irregularity of polyester cotton or any fiber blended, synthetic fiber blended with cotton. Okay. So, that's the, these are the formula one can directly use to get idea about the limit irregularity. So, for wool, the limit irregularity, as we have seen from the mass variability of fiber, that fiber mass variability was around 50%, 50-51%. So, this has come here to 112 square by n, and also we can get the limit irregularity for wool in terms of diameter variability. So, when wool fiber diameter variation is taken into account. So, if we take the wool fiber diameter into account, in that case the variation we can calculate, we can measure the variability of wool fiber, the limiting irregularity. This is the formula, that this standard formula we must know. Okay. So, for VR, okay, VR square of wool equal to 100 by 100 square by n, and then multiplied by 1 plus 0.0004 multiplied by V d square. This V d is nothing but CV% of diameter, CV% of diameter of wool, and it has been observed that CV% of diameter of wool is approximately 25%. Okay. So, diameter CV is approximately 25%. So, that diameter CV for wool, if we actually replace here by 25%, so 100 square by n 1 plus 0.0004 multiplied by 25 square, this value, this total value will be typically around 1.12. This value will come out to be 1.12 approximately. So, if we take 1.12 square, sorry 1.12 square this value, so then it will be actually 112 square by n. So, this value will be 1.12 square. So, it will come out to be 112 square by n. So, V R W is coming out of same. So, from the mass variation of wool fiber or diameter variation of wool fiber, we can get the same value of 112. Okay. So, one may ask a question. So, if the equation 112 square by n is given, then what will be the mass variation of wool fiber? So, one can calculate by back calculation. Okay. So, V d is the CV percent of fiber diameter, and when wool fiber diameter variation is taken into account. So, this is the formula, and CV of wool per fiber diameter is approximately 25%, and if we replace this. So, this will come out to be 112 square by n. Okay. So, what we have discussed the limit irregularity, or what our machine can produce, okay, for synthetic fiber, for cotton fiber, for wool fiber, or for blends. Okay. So, with this concept we can calculate many parameters, many ethics, the performance of machine, spinning machine, individual spinning machine, those we can all we can calculate everything. So, in next class we will discuss the all this calculation and how we can actually judge the performance of different spinning machines. Till then, thank you.